For today's agenda, we will start with a discussion about the DC voltage source, an ideal one versus a real one. And then we'll do the output impedance of a voltage regulator module. We'll talk about the NISM method, which is the non-invasive stability measurement. After that, we'll go over, talk about what's about from the power to the load, and measuring the output impedance. After that, we'll show you a few examples how to do the measurements, and that's it. Okay. So we'll hand over to Florian, who will do the first part of the presentation.
Good. So let's jump into the topic. Today we are going to talk about output impedance, and first of all, we are talking about output impedance of voltage regulators, and the goal of a voltage regulator is actually to provide a voltage source, normally in this case a DC voltage source, or probably even an AC voltage source. That is, so then it would be an amplifier or a controlled regulator where the set point is changing. We will now assume that the operating point stays constant, so we're talking about DC voltage sources. So about a device that maintains a fixed DC voltage. Ideally, the voltage of a voltage source doesn't change when you change the output current. So when the load current changes, the voltage will stay the same. This means that the internal resistance is zero and the output voltage is the same as the source voltage. In reality, there is always some resistance at the output, some source resistance, and that means that when you increase the current, then the voltage drops by the source resistance or by a trace resistance or whatever. It's a parasitic resistance. So that's one of the main reasons why the output is stabilized by using voltage feedback, or it's also, you can also look at it like that. So the output voltage is measured compared to reference, and the controller reacts to change the power stage such that the output voltage meets the desired output voltage, even though there is a loss somewhere. Of course, this control loop has some dynamics or dynamic behavior, and the loop gain, the T of S that we have drawn here, changes the output impedance of the power stage from the open loop output impedance to the closed loop output impedance. So closing the loop changes the output impedance of the power stage. And if you work out the math, or if you look it up in a book, then you will see that the closed loop output impedance, and we call it Z out here, equals the open loop output impedance divided by 1 plus T. So there is again the 1 plus T in the denominator. So when we look at that equation a little bit more in detail, we can see again, if the T is a large number, that will mean that the output impedance in closed loop case will be a lot lower than the output impedance in the open loop case. So the loop gain changes the output impedance, it lowers it. The higher the loop gain, the lower the output impedance. If the loop gain is a small number, meaning that the control loop doesn't have much effect, then of course the output impedance in closed loop will roughly equal the open loop output impedance. And in a very special case where the T is 1, then it will just be half of it, theoretically, because in reality there can be a resonance peaking that we'll talk about later. So a high loop gain results in a low output impedance. The loop gain at DC, however, is not infinite. That means that the output resistance or the low frequency output impedance will never be zero. There will also always be some finite value. Then the control loop is not infinitely fast, and the loop gain reduces with frequency. This means that the output impedance in closed loop case normally rises with frequency. There is some crossover frequency that we know that's going to be the natural frequency of the closed loop system. And of course, the control loop affects the output impedance mainly below the crossover frequency. And above the crossover frequency, where the loop gain is going to be small, the control loop doesn't have much effect on the output impedance anymore. So from there on, it's more passive decoupling then. A typical output impedance, a typical loop gain curve could look like that. That's a simulation of a buck converter linearized model, and the crossover frequency of the control loop is 40 kilohertz, and a phase margin was chosen to be 30 degrees. That's a voltage feedback, so simple voltage mode. You can see the resonance from the LC output filter in the loop gain, and the DC gain was limited to roughly 70 dB maximum gain from the error amplifier, for example. So that's why the loop gain starts to flatten out in the very low frequency range. It doesn't continue to rise to infinite number at DC. It flattens out at 70 dBs of maximum gain here. And if we use the same model, so that's the small signal equivalent circuit model of the back in closed loop case, you can see that's the plant model here. You can see the LC output filter with some parasitics here. The capacitor at the output is 330 microfarads with 10 nanohenry parasitic inductance and 48 milliohm series resistance, ESR. The inductor is a 5 microhenry inductor with 10 milliohms of resistance. And then we have the load resistor here. The compensator, a type 3 compensator, that is controlling the loop. And the output impedance was simulated by using an AC current source at the output that draws a 1 amp AC current over frequency. The current is measured with that meter. The voltage is measured in addition, and then we will get an output impedance plot in the closed loop case as well in the open loop case, where just the controller or the duty cycle stays constant, or the duty cycle ripple actually is 0 in this AC modeling. So from that model, and by the way, that model was done in Cooks, I don't know how to pronounce it. It's a quite universal circuit simulator, an open source circuit simulator, where this model was done. And when simulating the output impedance, in the two cases, so in the open loop case, that's the red curve here, and the closed loop case, that's the blue curve here, then we can see the loop gain, the influence of the loop gain on the output impedance. So on the right hand side, there is the loop gain plot here, and on the left hand side, the two output impedance curves over frequency. So in the low frequency case, at 10 Hertz, for example, there is 70 dBs of gain in the loop gain, and that drops the output impedance to a very low value, the output resistance in that case at very low frequency. And the higher the frequency gets, the lower the gain gets, because the loop gain is falling with frequency, and that means that also the difference between open loop and closed loop output impedance is lowering with frequency, and the closed loop output impedance starts to rise with frequency. And we're gonna now call that the effective output inductance. It's somehow like an inductance. It rises with frequency. Impedance rises with frequency. So from outside, it looks similar to an inductance. That's why a VRM is often modeled by a resistor and an inductor for some power integrity simulations. But then there is a very interesting thing. At the crossover frequency, in this closed loop case, the output impedance peaks. So it's even higher than the open loop output impedance. So the closing the loop causes an oscillatory behavior that can be seen as a peak in the output impedance at the crossover frequency of the loop, which is the natural frequency of the closed loop system. In this case, there was a phase margin of roughly 30 degrees, and you can see that there is some peaking visible. So from that, we can actually conclude that the output impedance plot contains information about the control loop stability, because it contains information about the loop gain. If the phase margin is low, there will be some peaking visible in the closed loop output impedance. And that's the basic idea of the NISM, the non-invasive stability measurement. And this was brought to us by Steve Sandler from PICOTEST. He actually explained it to us already, I think, 10 years ago. And now we start to understand what it is about and what's the background behind that. And we're going to share that information with you right now. So the basic principle from the NISM measurement is that the Q of the closed loop system, so the quality factor of the closed loop system, correlates to the phase margin. And the peak in the output impedance, of course, correlates to the Q of the closed loop system. So the higher the Q is, the higher the peaking will be. And the higher the Q is, the lower the phase margin is, because the phase margin is a measure for the damping of the closed loop system. An example here, that's a linear regulator that was measured over frequency. The red curve is the output impedance, and the blue curve, that's the QTG. That's actually a Q, so a quality factor derived from the phase derivative over frequency. And why is that the case, or why do we use the QTG? Because the phase turn is a very good indicator for a Q. If you have a resonator with a high Q, then the phase will turn very fast over frequency, or very, very sharp phase turn. If the Q is very low, the phase turn will be more shallow or slower, and then the Q can be measured very nicely using the first derivative of the phase over frequency. That's the case in this QTG measurement that you can do with the Bode 100. So let's look at the output impedance curve. At low frequency there is some finite output resistance because of the maximum loop gain. Then we have the effective output inductance that kicks in because the loop gain is falling. Then we have somehow a resonance that is formed between the effective output inductance and the output capacitor, and a Q, a peaking of that resonance that's caused by the control loop. And the lower the Q, the higher the phase margin, and in the end, at higher frequencies, that's basically above the crossover frequency of the control loop, there is just passive behavior. That's, for example, trace inductance in that case. So from this Q, from the height of that Q peak at the output impedance peak, so we need to find a peaking in the output impedance, in the closed loop output impedance, and there must be a Q peaking, and from that Q the phase margin can be derived using that expression. You can look up the equation in, for example, in Maximowicz and Ericsson's book Fundamentals of Power Electronics, and or you just use it how it's built in the Bode analyzer suite. That's the phase margin calculation, and if you put the cursor at the peak in the Q, then the Bode analyzer suite will give you the phase margin that correlates to that Q. So that's actually a very nice thing, because you can just measure the output impedance of a voltage regulator and then estimate the phase margin based on the peaking in the output impedance that comes from the control loop that has maybe insufficient damping. So in this case, at 22 degrees of phase margin, there will be a clear peaking visible. Of course, the higher the phase margin gets, the less peaking will be visible. We will also see that later on in the hands-on measurement. At the phase margin above 60 degrees, the peaking will barely be visible. Above 70 degrees, there will be no peaking at all, because it's critically damped or even over-damped. And you won't be able to apply that method to systems that have a very high phase margin. On the other hand, it doesn't matter too much, because if you have a high phase margin, you don't need to worry about the phase margin. And if you see a peak in the output impedance, then you need to worry, and then you can apply the method. Of course, there is more from the VRM to the load. So finally, actually, we want to bring the power from the VRM to the load. And there is more. There's not just the voltage regulator. There is always the voltage regulator, in this case modeled as an LRC network, and some trace. So there could be a trace that has some trace inductance and of course some copper resistance, probably some capacitor, some second capacitor with some C and R, then another little trace with some inductance and resistance, and probably another decoupling capacitor closer to the load, and then the load. And from here on we assume that the load is not a DC load, but it is a switching load or a transient load. So it could be a microprocessor that switches on outputs, or it could be an FPGA or whatever. So the load currents will be transient load currents that maybe have really sharp edges, and that's why it's important to properly decouple that stuff, that the transients don't disturb the voltage too much, the current transients. If we look at that diagram or that circuit schematics, of course there is 1, 2, 3 inductors and 1, 2, 3 capacitors and some resistors, luckily, to damp all the stuff. But if you use ceramic capacitors, these resistances can be pretty low because the ceramic caps have a very low resistance normally. And if there are ferrites, they also normally have very low resistance. So you could achieve very high Qs of resonances, and then it could be a problem. So we're going to look into that a little bit later. There is a little simulation example that we have done for that. So you see on the left hand side the VRM block, that the closed loop buck converter that has been simulated before on the previous slides, and then a trace with 100 nanohenries, so some centimeters, probably 10 milliohms of resistance, then a capacitor 4.7 microfarads with 20 milliohms ESR and 8 nanohenries inductance, then another shorter trace with 10 nanohenries and 3 milliohms, then another capacitor with 100 nanofarads and 10 milliohms and 4 nanohenries. So that's probably a ceramic capacitor here, a smaller one. The left one is a bigger ceramic capacitor or a tantalum capacitor. And then the voltage at the load, and the load here modeled as a sine wave load to measure the output impedance. So if we simulate what the load sees, so measuring the output impedance at the point where the load is connected, then it looks like that. So this simulation goes from 10 Hertz to 10, 20, 30, 40, 50 megahertz. And you can see that there are low frequencies up to 10 kilohertz. Everything is fine. It's a very low output impedance of a couple, like 15 milliohms. And then the impedance starts to rise. There is a first peak of the control loop, and this peak now depends on the phase margin of the control loop. So if we have a 10 degrees phase margin, the peak will be significantly higher than in the case of 30 degrees or 45 degrees or 60 degrees or 70 degrees. So that's different compensators with the same crossover frequency. So they all were at 40 kilohertz crossover frequency, but the phase margin was changed in the compensator, and you can see that at 10 degrees phase margin there is really a high peaking in the output impedance, a high Q peak. And at 30 degrees there is still a peak. At 45 it starts to get away, and at 1670 there is no peaking visible at all anymore. Then there is a second peak, that's the 4.7 microfarad capacitor with the trace and the VRM that's resonating there, and then there is an even higher high Q peak, that's the 100 nanofarads capacitor with the ESL and the trace and the ESL of the 4.7 microfarad capacitor. So there are multiple peaks, and let's simply assume that we have a 200 kilohertz load current that is going on, like it's switching with 200 kilohertz at the load, something. Then let's look at the 200 kilohertz. That's here, that's the 4.7 microfarad peak, so that's this peak. And here we have roughly 100, 200, 300 milliohms of source impedance. And at 3 megahertz load, so if there are 3 megahertz content in the current, then 1, 2, 3, at 3 megahertz we are nearly at 3 ohms. So and that's then, or at 3.5 megahertz, something like that. So there is a factor of 10 in between, and at frequencies below 10 kilohertz we are at 30 milliohms and lower. So this means that if the load current, the 200 kilohertz load current, for example, has 1 amp, then it causes either a 0.3 or a 300 millivolts drop at 200 kilohertz, or even a 3 volt drop at 3 megahertz. So, well, practically at 3 megahertz, this system won't be able to deliver 1 amp transient currents that have a transient content with 3 megahertz. Also for the 200 kilohertz, there will be significant voltage drop. For slower transients, of course, it's not such a problem anymore. The peaks in the supply impedance, of course, have another risk, because the high impedance increases the risk of coupling noise into the circuit or into the supply voltage. If we assume that we have a constant disturber that has a constant disturbance power, that's the P, then increasing the resistance or the impedance causes the voltage to increase when we assume voltage is square root of power times resistance. So the higher the impedance peaks become or get, the more sensitive the system will be to coupled noise that comes from a constant power noise source. The noise, of course, can degrade the system, it can degrade oscillators, ADCs, reference voltages, and whatever, and we don't want that, certainly. There is another risk, and that's the risk of the so-called rogue waves. And a rogue wave is a superimposition of two frequencies that is somehow a worst case or a superimposition, so it's a constructive interference, I think, or I don't know, remember how it's called correctly. So this means that multiple oscillations add up on top of each other. So if you have dynamic load currents that have multiple frequencies, they could superimpose, and the worst case scenario is a rogue wave. And this picture we got from Steve Sandler, where he has measured a rogue wave. There are two frequencies, you can see two oscillations, a slow one and a fast one, and unluckily the fast one stacks up on the peak of the slower one, and you get double the amount. We are here at nearly 50 millivolts change in voltage just because of two transients that are both something like 30 millivolts, and then they stack up and you get nearly double the peak-to-peak voltage. So that's a risk that can then, of course, either destroy something or trigger something unwanted, and it's because two frequencies add up on each other at two peaks in the output impedance. There is only one way that you can use to really avoid such resonances and peaks, and that's the flat-impedance approach. That means that the source should represent a constant resistance to the load over frequency without peaks in the output impedance. So no peaking means a flat impedance over frequency. That's somehow like an impedance matching. And in addition, not only getting rid of all the resonances, it does also reduce the internal chip resonance. That's also sometimes called the Bandini mountain. That's the resonance of the bond wire with the chip package capacitance that no one can influence except the manufacturer of the chip, so it's inside of the chip. But by having a flat impedance power supply, the height of that resonance in the chip will also be reduced according to that simulation that we got from Steve Sandler. So it doesn't even reduce the risk of rogue waves outside of the chip, it will also reduce the height of the peak in impedance inside of the chip. So the output impedance plot contains information about the control loop stability, it contains information about the oscillatory behavior of the closed loop system. No matter if it's a switch mode regulator or a linear regulator, there is a control loop going on, and you can estimate the phase margin of that control loop. It reveals resonance frequencies of the decoupling network, and these peaks can cause performance degradation of the load that is supplied by that system. So I think it contains a lot of information, and it's not so hard to measure, so we're gonna measure the output impedance from now on. And Tobias will now present you some possible measurement setups for output impedance measurements.
So let's start with some examples how we can use the Bode 100 to measure the output impedance. For example, if you have voltages smaller than 3.3 volts, DC voltage, then no special precautions are needed, since the Bode 100 output can handle or withstand that voltage. At the Bode 100 output, there's a 50 ohm resistor, which is able to withstand a maximum voltage, I think, of 5 volts, but we recommend 3.3 volts DC as a maximum. Therefore, the possible measurement methods that you have are, first, the easiest one port impedance measurement. You can use a shunt through measurement or the extended shunt through measurement method. This is recommended for very low impedances. Then also a very easy one setup is using the PICOTEST current injector J2111A, or you can use every alternative load modulation. and examples. The one-port method, so only the output of the Bode 100 is connected to the output of the VRM. That's the easiest setup, but it's not really suitable if you have very low impedances in the milliohm range. We will also do a live measurement afterwards using the one-port method. The two-port shunt-through method is as I told you already, is the best suitable one if you have very low impedances in the milliohm range. But if you measure at low impedances and low frequencies, please take care of the ground loops. To do so, use, for example, a common mode choke or differential amplifier. Additionally, you can use an amplifier at the output of the Bode 100 to get more signal into the system, to also get a better signal-to-noise ratio and get cleaner results. Oh yeah, furthermore, both of these methods can be used to do an off-state measurement of the impedance. So measure the output impedance of the VRM without power supply, without input voltage. If you have voltages smaller than or up to 42 volts DC, then you can have to take care of the Bode 100, especially the output, or just only the output at 42 volts, the output of the Bode 100, since there is a 50 ohm resistor which is AC coupled.
Yeah, also in the input, if it's set to 50 ohms, you cannot connect 42 volts, but if they are set to high impedance, they can withstand up to 50 volts. So then that's not a problem.
So to do so, you can use the current injector. That's the easiest method if you want to measure up to 42 volts. Then you can also use the one port with a DC block. If you do so, you need to do a calibration to remove the influence of the DC block. Then you can use shunt through. There you need two DC blocks, so at the output and at channel 2. Also, here you need to do a calibration to use the influences. You can also use shunt through measurement, the extended shunt through measurement method, where you have series resistors. These series resistors will divide the DC voltage, therefore you do not need DC blocks. But as well, you have to do through calibration or open short low calibration to remove the influence of these resistors. Additionally, you can use all alternative load modulations where you can protect the Bode 100. Here you can see the measurement setup using the PICOTEST current injector. There is the modulation input where the Bode 100 is connected, a current monitor to measure the current that flows, that is drawn from the output of the VRM, and then you have channel 2 where you measure the voltage, then you have a voltage in the current signal where you get the impedance. The setup is very simple. We will also show that afterwards in a short example on live measurement. Nice to know is that the current injector draws a DC current of 25 milliamps plus additionally an AC current which is 10 milliamps per volt. You can also use a dynamic load. You have draw AC current or AC and DC current depending on your dynamic load that you have. There you need a current probe as well as a voltage probe to get the impedance. If you have voltages higher than 42 volts, first of all, please be aware that these are very dangerous voltages and protect yourself as well as the Bode 100. You have a few different possibilities to do these measurements. Using the voltage current method and using a power amplifier. This example we have an amplifier from Rohrer in Germany. You can set the DC, use the output of the Bode 100 to modulate the current that is drawn, and then also you need a current probe and a differential probe or an isolation probe to protect the Bode. Additionally, they have the alternative load modulation possibilities. first of all, the inductive injection. So you use the output of the Bode 100. Additionally, there's an amplifier to inject a higher signal, to get a better signal to noise ratio. Then you can use any inductive. You can build one for yourself, for example, or buy one. It provides a galvanic isolation, but if you have high DC voltages, you also need a big transformer which does not saturate at the DC currents that you have. Did I say voltages? DC currents. As I mentioned, the amplifier at the output to get a higher signal. You can also use capacitive injection. It requires a big capacitor if you want to go to low frequencies. It's really hard to get one. If you want a big capacitor which also withstands high voltages or currents, voltages. And additionally use an amplifier at the output of the Bode 100 to just get more signal. So next we will do a hands-on example. I think Florian will tell more about that.
So as our first hands-on example, we will use the VRTS 1.5 board from PICOTEST. That's a linear voltage regulator, a positive voltage regulator that uses a TL431 for the controller. So here is the input, on the right hand side is the output. There is the power transistor that burns the voltage, so it burns the voltage down from 7.5 volts input to 3.3 volts output. Then here is the feedback divider. It goes into the TL431 that drives the power transistor. At the output we have two different output capacitors where we can choose between 100 microfarad tantalum and 100 microfarad aluminum capacitor. And we'll use the very simple setup, the one-port impedance measurement setup. So the output of the Bode 100 is directly connected to the output of the linear regulator. It's only 3.3 volts, so we could connect it directly. We have introduced a DC block to show how that setup works if you have a little bit higher voltages. Of course, if you have higher voltages, please take care that you don't have transients that pass through the DC block, destroying the Bode 100 output. There you have to be careful. So we're going to do the measurement now and bring on the camera, and Tobias will explain the setup and configure the measurement. And the first thing we need to do afterwards is to make a calibration to get rid of the DC block in the measurement path.
Okay, first of all, here we have the power supply. It's the 7.5 volts for the linear regulator. Then on the right hand side of the module we have the output connector. Then we connect our probe with our self-made DC block to the output of the Bode 100. And then for the measurement setup we would only need to connect these probes to the output of the Bode of the VRM. But before we do that, we will do open short load calibration at the end of the BNC cable.
Okay, for that I'm gonna start the Bode Analyzer suite and select the one-port measurement method. And the first thing that I'm gonna do is to choose the frequency range of interest. So 100 Hz start frequency, I think that's a good choice, and we'll go up to 10 MHz stop frequency on a logarithmic scale, 200 points, that's sufficient. I'm going to use the full output level of 1 volt RMS of the Bode 100 and set the receiver bandwidth to 100 Hz because that gives us a pretty fast sweep with a good noise rejection. And the first thing is we're going to do a user range calibration. In that case, to get rid of the frequency response of the capacitor, it makes sense to use the user range calibration because it does not use any interpolation. So the first thing is the open state impedance. So Tobias has nothing connected to the BNC cable, and I'm going to press open now, and the Bode 100 measures the open state impedance. That's done, and Tobias is now connecting the short connector.
Now we'll connect the short.
And we click on short. And then the load connector, please. That's a 50 ohm BNC terminator. And we click on load. So now we're done, and we can connect the DUT.
I'll disconnect the 50 ohm load resistor, connect our two short wires, and now I can connect it to the output of our device under test.
Of course, our measurement will still include the inductance of that connection, so of the last connection that we didn't calibrate. But for the control loop measurement, in that case, that doesn't matter too much, because this will have an influence on the trace inductance that is going to measure later on, but we don't measure that value directly. We want to see the stability of the control loop, and there these couple of nanohenries or hundreds of nanohenries don't care, or we don't care about them too much. So Tobias has switched on the power supply, 7.5 volts input at 35 milliamps. The LED is shining blue, so the system is running. And what capacitor do you have connected right now?
Now we have the tantalum.
Okay, perfect. So I'm gonna switch back to the Bode and start a continuous sweep. Something is wrong, Tobias.
Probably might be an error in the calibration.
Can we do the calibration again?
Check that first. We'll connect the 50 ohm again.
So 50 ohm, that's perfect.
That's
That's
fine.
nice and flat. I think we do the short again.
Probably the open.
Open is beautiful. Short again, please. Yeah, good enough. Below a milliohm. And Tobias is connecting the DUT again and switching it on. And something is completely wrong.
That's very
What did we do?
interesting.
What did we do?
That's the output.
Ah, now it's working. There was a bad contact in the cable.
Oh, okay.
Good. Well, that's not so good, but yeah. So the cable that we use is not so nice, and we already see the drawback of the one-port method. The problem of the one-port method is that it's a two-wire connection, so it's sensitive to contact resistance, and the impedance that we are measuring here is below 100 milliohms in some points. So the contact resistance of bad connections can corrupt the measurement, but now the measurement looks nice, and we're gonna use the phase margin calculation to calculate the phase margin. So first let's have a look at the curve. We see at 100 Hertz there is a very low output impedance of, let's use the cursor and drag the cursor here. It's around 80 milliohms of output resistance. Then there is a peak in the output impedance at around 6 kilohertz. That's from the control loop. Then we see the impedance falling again, and in the end rising from parasitic inductance. And as I said before, the parasitic inductance of course will be too high, because we are also measuring the parasitic inductance of our connection leads. So to use the non-invasive stability measurement in trace 2, I switch from phase to the QTG. And then I click optimize here. And here we see now on the y-axis the QTG, and the Q is peaking at the same frequency where the output impedance is peaking. So I place a cursor here, and we see that the Q is roughly 1 at that peak. And so we use the cursor and say basic phase margin calculation. And here we get a result of roughly 40 degrees. If we put the cursor at the peak of the Q, it's around 40 to 50, 45, 53 degrees of phase margin at the impedance peak. So the phase margin is still pretty nice, but the output impedance peaks a little bit using the 100 microfarad tantalum capacitor on that linear regulator. I'm going to put that to memory, and we'll now switch from the tantalum capacitor to the 100 microfarad aluminum capacitor. So same capacitor, but of course a higher ESR. And by switching the capacitor from tantalum to aluminum, the peak has completely disappeared now. As you can see in the new measurement, there is no impedance peak anymore, and also the Q is never above 0.2, or it's around 0.16 or something like that. So that we are not able to measure a phase margin anymore because the Q is now so low. The system is well damped. The linear regulator in this case likes the ESR from the ceramic capacitor. It gives it more damping in the control loop, and the peak in the output impedance did disappear. And that's a very, very fast and simple measurement that can be easily done on nearly any linear regulator on a board, because you just need to connect to the output capacitor of the linear regulator. There are even professional probes for that. PICOTEST has the PDN probes, 1-port and 2-port probes, that should allow, or that allow a better connection if you don't have the nice test pins that we have at that board. If you really need to connect to the output capacitor directly, then you can use special probes for that. So I'm going to switch back to the presentation. We have done that measurement, and as a next measurement we will use the same board that we used in the previous webinar, where we measured the loop gain of a SEPIC converter with a modified control loop. Please don't forget, I have made the control loop worse than they did on the demo board. On the demo board, actually it's a really good control loop, but we have corrupted it by changing the compensator network to give it less phase margin. And we're gonna now use the PICOTEST J2111 current injector, because that's a 24 volts regulator, and there the current injector is really handy. So the setup is using the current injector connected to the output of the SEPIC converter, and Tobias will now make that setup and explain the setup that we have in here.
First, here we have our demo board. On the left side, it's the input voltage is connected. On the right hand side, we have the output load and two digital multimeters to measure the output current and voltage. So for the setup, we do have the PICOTEST current injector. So the output of the Bode 100 is connected to the modulation input of the J2111. Then the current output, or the current monitor connection, is connected to channel 1 of the Bode 100. And on channel 2 of the Bode 100, we now have to connect a voltage probe, which is connected to the output of our device under test.
In this case we use a 10-to-1 probe. We could still use a 1-to-1 since it's below 50 volts, but we use the PML 10-to-1 probe. It just provides better protection to the inputs, and we don't want to break stuff during the webinar.
Before I put on the probe, I will connect the current injector to the output of the voltage regulator, so it's easier for the setup for the connection.
Okay, so Tobias has managed to clip on the probes and is now switching on the system.
Switching on the power supply, we have 40 volts input, output current is 0.3 amps, and the output voltage is the designed 24 volts DC. So now we can go over and go into the Bode Analyzer Suite and do the setup.
Good. For this measurement setup, we need to start a new measurement. I say new measurement, and use the impedance analysis tab. And here we use the voltage divided by current method, where the channel 1 receives a current signal and the channel 2 receives a voltage signal. I'm gonna discard the previous measurement. We don't need that anymore. And first, in the hardware setup, I have to configure the channel 1 to have 50 ohm input impedance. That's a requirement from the current injector that delivers a 1 volt per amp signal at the monitor when terminated into 50 ohms. Then at channel 2, I selected 10-to-1 probe because we have connected a 10-to-1 probe. Then again, selecting the frequency range, we're gonna measure again from 100 Hz to 10 MHz. As before, now in this case it's not so important, we go to 1 MHz. We are now in the switching regulator, SEPIC, the control loop switches, or the switching frequency is 300 kHz, so actually it doesn't make much sense to measure the control loop above half the switching frequency, but I'm gonna measure up to 1 MHz to see some trace inductance in addition. Then the source level, here we can use the maximum power because the current injector will give us then roughly 20 milliamps modulating AC current. That's no problem for the 1 amp regulator system. Gonna reduce the attenuators. I don't think that we need them, otherwise we can increase them again, and I set the receiver bandwidth to 100 Hz. And then I think we're done, and I start the measurement. So that's how the output impedance looks like. At low frequencies it's very low, it's around 10 to 12 milliohms. Then it starts to rise to 100 milliohm, up to 200 milliohm. I'm gonna switch trace 2 to the QTG, so the Q derived from the phase. It's mostly noise, so there is no high Q. We don't see a high peak in the output impedance. The phase margin is probably quite high in that case. I'm gonna switch on the stability margin calculation, the phase margin calculation, and it says at cursor 1, something like 70 degrees. So everything looks pretty nice in that case. And I'm gonna store that to the memory. And now we'll try to change the operating point to find a really bad phase margin case where we have a lot of peaking, or we should have peaking in the Q. So if I remember correctly from the previous webinar, when we went to 1 amp load current and minimum input voltage, there was a really bad phase margin left. So Tobias, can you please change the operating point?
So increase, change load so that we have a higher output current. Now we have 1 amp at the output.
So now we have switched from 300 milliamps to 1 amp, and if I move the cursor to the peak in the QTG, then we are already at roughly 30 degrees of phase margin, so things have gone a little bit worse, and we're gonna now lower the input voltage to the low input voltage where the phase margin should be even lower. Tobias, can you please lower?
So the input voltage is now at 20 volts.
Okay. So now the peak in the Q has gone very high. Also the peak in the impedance is now very high. We can see a peak in impedance up to nearly 1.6 or 1.7 ohms, impedance. So nearly 2 ohms of impedance at 20 kilohertz, which is not a really good supply in that case. And the phase margin calculation at the peak in the Q is now indicating a phase margin of roughly 9 to 10 degrees. And that matches exactly what we have seen in the previous webinar, where the loop gain measurement did show 9 degrees of phase margin at 20 volts input and 1 amp output current. So the advantage of that measurement, of the non-invasive stability measurement, is that you don't need to break the loop, you don't need to insert an injection resistor, actually you don't even need to find access to the loop. You can just access the output of the regulator, and if there is a phase margin issue, so if the phase margin is too low, there will be a peak in the output impedance that you can use to estimate the phase margin. Of course, it does not really tell you, and Tobias has now found an even worse point. So here the peaking, now we start to hear noise. It's only 6 degrees of phase margin. We start to hear that the system is generating even noise at that frequency. So, what did I want to say?
I'm sorry for the interruption.
So it's very nice because if the system has an issue in the control loop, you will see it immediately in the output impedance measurement, and it only requires 2 points to be connected actually. So that's pretty nice. That was the measurement from our SEPIC converter. I think we can turn off the poor SEPIC that is disturbed at 6 degrees of phase margin and switch back to the presentation. I have one example that we did prepare previously and will not run it live because it's a little bit more effort, and tried to analyze a very, very cheap USB scope. That's the USB scope that we tried to measure. It has 2 channels, channel 1 and channel 2. And the input connectors, the BNC connectors, you can see on the left hand side, marked with 1 and 2. Then there are the 2 channels, and then the system has a single ADC, a 2-channel ADC that picks up the signals, and the ADC is supplied by this LDO that converts the 5 volts from the USB to, I think, 3.3 volts for the ADC. So let's have a look at the power supply of the ADC. There is the LDO on the bottom right hand side. Then it goes through some filtering. You can see C, a bigger C, an L, a C, and a C. Then on the bottom side, it continues to go over the trace to another filter that is very close to the ADC with C, L, and C. And then it's connected to the ADC, and there is an additional decoupling capacitor, the C63, that is directly at the supply pin of the ADC. So the LDO, a first filter, a second filter, and ceramic decoupling capacitors directly at the ADC. We did measure the output impedance using a 1-port probe and tried to connect very close directly at the decoupling capacitors of the ADC, and used a DC block to protect the Bode 100 and a 1-port impedance measurement to measure the output impedance. And the plot looked like that. So from 1 kilohertz to 50 megahertz, the output impedance is not really low. It's about 200 milliohms. And then at 100, 200, 300 and 350 kilohertz, there was a really high peak in the output impedance. That's around 10 ohms or so. And that's mainly caused by resonances between the ferrites and the ceramic caps in the filters. So if we bring in a 400 kilohertz disturbance, like there was this little coil, it's a wireless power coil, and we did drive the coil with 400 kilohertz from an arbitrary function generator just to bring a 400 kilohertz magnetic disturbance close to the power supply. And in the ADC result from the scope, so that's the FFT result of the scope, blue is channel 1 and red is channel 2, the 400 kilohertz disturber could be clearly seen at roughly minus 60 dB, so the noise floor of the system was at minus between 85 and 95 dB, and the disturber was roughly 30 dB higher because it was coupling into the result of the ADC. So the 400 kilohertz disturber inductively coupled onto the supply line, or not directly the supply line, but onto the system actually, close to the supply trace, did clearly show up in the ADC. And then we have made a short circuit of the Ferrite bead. So just putting on a jumper over the Ferrite bead to short the Ferrite bead. And the disturber was the same, but it didn't show up anymore on the ADC data. So you can see it's still there, but it's roughly 2 10, 20, somewhere like 25 dBs lower than before, so like 20 times smaller than before. So I will bring back the picture from before and after. So you can see the disturber is not showing up in the measurement result as strong as before. And what we can see in addition, if you look at the noise floor, now the noise floor is around 90 to 100 dB. That's pretty interesting as well to me. So I go back 85 to 95 and now forward 90 to 80. Backwards 85 to 90, forwards 90 to 100. So we also won roughly 5 dB or 4 dBs of noise floor by removing the ferrite bead directly at the supply of the chip. So what did happen to the output impedance? What has changed in there? You can see in blue the output impedance curve from before, and in red new output impedance curve with the shorted ferrite. So it has dropped by a factor of 20 roughly at the 400 kilohertz. That's why the disturber also has dropped by a factor of roughly 20 in the FFT result, and the entire curve did move a little bit lower in total. I assume that's the reason for the lower phase, the lower noise floor in that case. But at 1 point or at 2 megahertz we made it worse, so there one would need to improve a little bit more to optimize the system further. So in summary, the output impedance reveals a lot of information about the control loop stability and resonance frequencies in the supply line. It is simple to measure. The output capacitors are nearly always accessible. You don't need to break the control loop, and only the flat impedance guarantees optimum damping at all frequencies, avoiding resonances that could cause rogue waves, and lowering the output impedance results in less noise in the system. There are some further readings and references that you can have a look at